Section 6.2. We are going to talk about parallelograms. Yeah. Parallel, that's how we spell it. Make sure we spell it right, please. Okay, so parallelograms. Did I spell it right? I think I did. Two L's and one L. Okay, it goes two L's then one L. Parallel, and then ograms. That part's easy, isn't it? Ograms. So this whole chapter is about quadrilaterals. What basically is a quadrilateral? It's just a polygon with what? More than three? So if it has 7 sides, that's a quadrilateral? Exactly 4. Quad. Quad meaning 4, okay? So a polygon with 4 sides is a quadrilateral. Look, this could be a quadrilateral. I'm just making one up. See how crazy it looks? That's crazy looking. Okay, that's a quadrilateral. It's because it's got 4 sides. Okay, nothing has to be equal to each other or anything like that. So long as it's got 4 sides and it's a polygon, it's a quadrilateral. Parallelogram, we're getting a little bit more specific. So let me draw you an example of a parallelogram. Okay, that technically is a parallelogram, but I'm gonna draw one that looks a little more like they do in the book. So let's go like 20 degrees right here. Okay, that's when they show a parallelogram in the book, they usually make it look something like this. Okay, that's a parallelogram. Well, why is it? Let me scooch it over a little bit. Okay, why is it a parallelogram? Well, look for the definition, right? Look to the definition to find out why it's a parallelogram. Here's the definition. Now, you don't have to memorize it word for word, but I would like you to know what the definition basically says. And the definition says something like this. It says it's a quadrilateral, the definition of a parallelogram. It's a quadrilateral with both pairs of opposite sides parallel. Does that make sense? So if I call this A, B, C, D, all right, both pairs of opposite sides are parallel. So that means AB would be parallel to DC. That's one pair of opposite sides. Everybody got me on that? Now, if that was the only thing I knew, I couldn't call that a parallelogram. What has to be true? Not just one side is parallel, what? Both pairs of opposite sides are parallel. Now, we do have a word that we're going to learn later on in the chapter when only one side is parallel. Okay, but that's not what we're doing today. We'll get to that later. So watch. If these two sides are parallel to each other, they're opposite to each other, aren't they? So if these two are parallel and these two right here are parallel to each other, guess what I have? I got a parallelogram. Let's write it down. So what must be parallel as far as using all the letters and stuff? Let's be more specific about this parallelogram. Well, if this is a parallelogram, what do we know so far? That AB, what? Line segment AB is what? Come on. Congruent. Did we say congruent? Parallel. Okay, it's parallel. AB is parallel to what? DC. Okay, what else is parallel? AD is parallel to what? BC. All right, that's by definition. Okay, it's not a theorem, it's not a postulate, it's definition. Okay, the definition of a parallelogram says that the opposite sides are parallel. It doesn't say anything about it being equal, doesn't say anything like that, does it? Okay, the only thing it says is that the opposite sides are parallel. That's by definition. But we do have a theorem. All right, so the next things we're gonna jot down about 4 more things. These are theorems. It's just my abbreviation for theorems, okay? So here's some theorems. Let's do the first theorem. The first theorem says this, and let's do this in not that you can really see much difference in the color, but if this side, well, not if it's a parallelogram, then what's true about the lengths of the sides? What do you think? Just eyeballing it, what do you think's true about AB and DC? Say it. They're congruent to each other, absolutely, okay? It's not because of the definition, but it's because of a theorem. All right, so these two opposite sides are equal, and guess what? These two opposite sides are equal to each other. So the opposite sides, for our first theorem, opposite sides are equal to each other in length. Pretty easy, isn't it? Yes. Yes, it is. Let's write that down. So I could say that what? AB, according to what I just said, what? AB is what? Come on, let's look at it. Look, AB is what? Right, it's congruent to DC. Now I could say congruent, I'm just going to say equal. If I don't put any line segment over top of it, it means the measure of AB, or the length of AB, is equal to the length of DC. Right? If you see in the book, they'll put a little line segment over top of it, a little squiggly here for congruency. Either way, I'm perfectly fine with. Is that the only thing that's true, is just these two sides are equal? No. what else is true? That AD is also equal to BC. All right, equal to each other in length. These are two different things, aren't they? The definition says they're parallel to each other. The first theorem says the opposite sides are equal to each other. Well, there's something else that's true. Let's take a look. Look at this angle A right there. Compare it to some of the other angles. What do you think?
C.
Yeah, A and C. Exactly. Look, because this is obtuse. Now, A and D, there's no way they're equal to each other, is there? Because this is acute and that's obtuse. Look, this is obtuse as well. And they are, well, A and C are equal to each other. All right?
Would A and D be supplementary?
Well, we'll talk about that in a second. Okay, A and C are equal to each other. And so if A and C are equal to each other, what else do you think? D and B are equal to each other as well. All right? So what we say here is that the opposite angles are equal. All right? The opposite angles, A and C are across from each other. Do you see that? They're opposite angles. The opposite angles, right there and there, are equal to each other. So let's write that down. So this is our second theorem. So I could say that angle what? A is equal to angle C. It's a weird looking angle symbol, but there, it's okay. All right, so A and C are equal, and of course angle B and angle D are equal to each other. That's our second theorem. Okay. Here's our third theorem. Now, you guys already hinted at this already. Look at A and D. You got parallel lines, don't you?
Yes.
This would be considered a transversal. What kind of name do we give the relationship between these two angles right here, A and D?
Consecutive.
They're consecutive interior angles. Do you remember that one? And what did we say about consecutive interior angles? We said that they're what? That they're supplementary. Exactly right. So what we say is, watch. See how this one and this one are next to each other? They're not opposite to each other. We call them consecutive angles, all right? So the consecutive angles on a parallelogram are supplementary, not equal. Okay, almost slipped. They're supplementary to each other. So what can we say? We can say angle A is supplementary to what? Angle D and what else? Angle B. Do you agree? So angle A is supplementary to angle D, which means, you know what supplementary means. What's that mean? That they do what? They add up to 180. Good. So A and D add up to 180, and guess what else adds up to 180? A and B. You could also talk about angle C. Angle C is supplementary to what else? Angle D and angle B. That's right. So I could say angle D and angle B. Now that kind of makes sense, doesn't it? Because look, A and C are exactly the same angles, aren't they? So if A is supplementary to D and B, C is exactly the same angle, so it's got to be supplementary to D and B. Make sense? All right, that's pretty easy. And then we got one more. Let me draw another picture for this one, though. Look at this. Looks like a what? Looks like a rectangle. But we don't know it's a rectangle just yet, do we? We can only tell if it's a rectangle if what? If what's true about this angle. In order for it to be a rectangle, they got to be a right angle, okay? So what this theorem says is this. They only tell you one of the angles. I'll call it W, X, Y, Z. They only tell you, let's say, that angle X is 90 degrees. But from this information up here that we've already learned, if angle X is 90 degrees, tell me something about angle Y.
90 degrees also.
Why is it 90 degrees? Just tell me. Consecutive interior angles, okay, and they are supplementary. So 180 minus 90 is 90. So they're equal to each other. Okay? Or they're both 90 degrees. Now watch. I could have also said this. I could have said angle X is equal to angle Z for what reason?
Transverse.
Opposite angles. Remember what's true? Opposite angles are equal to each other on a parallelogram, aren't they? Okay? So for all kinds of reasons. I could say W is equal to Y because they're opposite angles. Or I could say that W is supplementary to Z, right? And that would still give you 90. Or I could say W is what? Supplementary to X. That'll still give you that to be 90. So all kinds of reasons. Do you see that? Why that's a right angle. So what the theorem says is this. It says if a parallelogram has one right angle. See, I only told you that it had one right angle, but I also did tell you that it was a parallelogram, okay? I said it's a parallelogram One of the angles is a right angle. What must be true about the other 3 angles? They got to be right angles as well. And of course, we call this a what? A rectangle, okay? We're going to do a lot more with rectangles a little bit later, not in this lesson right here. Okay? Pretty easy stuff, isn't it? Yeah. Let's do a little bit more. Let me see what I want to go. Yep, let's do this one. Okay, I've got another parallelogram here. Now, we've talked about this before. We talked about this just the other day. If I start from, maybe even yesterday, if I start from a vertex and I go to a non-consecutive vertex, what have I just drawn? What do we call that thing? I call that a diagonal, right? Okay, let's make that a different color. All right, that's a diagonal. Now watch. This time, I can only draw that one diagonal right here, but let's go over here to this one, and I wanted to draw another diagonal. All right, if I went to this vertex, I want to draw another diagonal. That would go to here. All right, so I've got 2 diagonals. Agreed? They intersect each other. Let's talk about that point of intersection right here. Let's just kind of eyeball it and look at it and take some guesses. Is that better? It's better now. Okay. So watch. Let's just take some guesses about this. Where do you think that point lies in comparison to these things right here? Let's call this Q, R, S. There, I used different letters this time. It's supposed to be a Q. All right. And we'll call this X. All right. So watch this. This point X right here. Where do you think it's located as far as line segment PR is concerned? Leah, what do you think? It's the midpoint. That's right. This is the midpoint of this line segment, which means that PX is going to equal what? XR. Where do you think this is compared to SQ? It's at that midpoint of SQ as well. That's right. So this segment and this segment. Does that mean that PR and SQ are equal to each other? No, absolutely not. Okay, this one right here is quite a bit shorter, isn't it, than this one right here, QS? So they're not equal to each other. The 2 lengths aren't equal to each other, but this is the midpoint of both of them. What's another way we could say it? That the 2 line segments do what to each other? Yeah, they intersect, but more specifically than that, they bisect each other, okay? They intersect each other, sure, but more specifically, they bisect each other because they split each other into 2 equal parts. Does that make sense? So that's what our theorem says. This is a theorem, and it says the diagonals, it says if you have a parallelogram, then the diagonals bisect each other. That's basically what it says. Okay? Make sense?
Yes.
Pretty easy. All right, enough of that. Let me do one more little thing. I forgot to mention this in my other class. So you guys are special.
Yeah, we're in favorite class.
Sure you are.
Don't deny.
I said sure you are. All right, look at this. Look at this SQ right here. That's a diagonal. What do you think might be true about these 2 triangles that are created right here? They are congruent to each other because let's see why. All right, this is kind of like a little mini proof. We know that this side and this side are equal to each other, right? Because I said it's a parallelogram, okay? I was given that this is a parallelogram. So those 2 sides are equal. What else is equal? This one and this one. Anything else?
And the
SQ is equal to
Yeah, SQ and SQ. There's all kinds of other ways. I could have said P and R were equal, right? Because if it's a parallelogram, the opposite angles are equal and all that good stuff, okay? So I could have gone side angle side, or this would probably be the easiest way to do it. Just say what? Side, side, side. So these triangles are congruent to each other. Make sense?
Yeah.
All right. So what does that mean then? That means that this angle, I'll tell you what, I'll do it like this. This angle right here, and probably this one over here, right? If I take it and flip it, those 2 would correspond to each other, and then these 2 would correspond. But look, what's true about big angle S and big angle Q?
They're bigger than brothers.
Yep. Am I skipping ahead a little bit? Hang on just a second. Okay, it's page 403, number 9 through 12, and 15 to 20.
Somebody want to hit me up with paper, please?
There it is. You got a lot of time. You got about 20 minutes in class to work on it, okay? So go ahead, get it finished.
That's right.
And just for the fun of it, I'm going to go over 15 minutes because I can.
Oh, yeah.
Alright, so, see, I'd be real scared right now before, but
We're
now,
just that awesome.
see, I got no problem going
No
over
danger.
15 minutes.
Okay.